Hello, class. This is Professor Carbone with section 1.5, the limit of a function. This is part one of the videos regarding this due to it being one of these more involved lessons where we talk about, in this case, a bunch of graphs, as you will see in a few moments. So without further ado, so a limit. And this is where we want to find the tangent to a curve or the velocity of an object. For example, when it comes to the applications we are eventually going to be looking at. We turn our attention to limits in general first, and the numerical graphical method for computing these limits, since once you look at the graph portion of it, the numerical tends to follow along with that a bit, at least in my opinion. But when it comes to finding the limit, right, before we specifically look at the graph, if we were to take a function such as the one I have here, f of x is equal to x minus 1 divided by x squared minus 1. And we look at a specific value. In this case, we want the value of x near, if I do not start drawing on this. In the process of that, and let me actually just get that on here so I can actually draw on it without me advancing the slide. So we want to see this near that value of x, near the value of 1. So what does that mean? Well, we want to be looking at values of x that are close to the value of 1, but not equal to 1. Why does that matter, right? Well, if we were to just look at this and we just put 1 into our function, we get a value of 0 in the numerator, which, well, technically not a bad thing. You see, if you put 1 in the denominator, you get a 0. This is not helpful in finding the value of anything. It's indeterminate in this particular case. The point, though, is we can look at values below the value of 1, such as 0.5, 0.9, 0.99, 0.9999, and so on, which starts getting towards the value of 1. And you could kind of see, if you were to plug those numbers into a function, you get these different values, right? We get something about 2/3. To begin with, if we put 1/2 into this function, 0.5263 about when we put 0.9, 0.5025, 0.500250, 0.50000025. See those numbers going down? I mean, mind you, slowly, right, as we're getting closer and closer to the value of 1, but we start approaching the value, as I have here, of 1/2. Likewise, if we put in values above 1 and start going down towards the value of 1 again, so 1.5, 1.1, and so on, as we get closer and closer, we again see these numbers approaching that value of 0.5. So even though if we put those numbers into it, we're getting a value here of 0, which doesn't, in both the numerator and the denominator, gives us nothing we could really go by. We could see just by looking at this table, we are getting close to values of 1/2. And as such, if we were to look at the graph, since sometimes the table isn't necessarily the easiest of things to be looking at, the closer we get to the value of 1, either here on the left-hand side or the right-hand side, right? Of course, we get to 1, we could see what's going down with this graph. We are approaching this particular value here. Now, mind you, if this was not already labeled for us, we wouldn't be able to determine it as nicely, but we're getting close to this value here of 1/2, which is the whole point, again, to see with that graph. As such, we can make the value of the function to be as close to a half as possible if we start taking values of x closer and closer to the value of 1. So because of that, it's approaching that value of a half as we get close to the value of 1 from either side. The limit as x approaches 1 of x minus 1 divided by x squared minus 1, we get ourselves a value of 1/2. So what does all that mean, right? Since, saying these different things is all nice and dandy, but let's face it, we need something we could work with. Definition of the limit. We could write that the limit as x approaches a of some function f of x is equal to capital L, or alternatively that the function f of x approaches L as x approaches a. And when we find the limit of f of x as x approaches a, just as we just did, we don't consider the value of x is equal to a. We only care about how a function behaves or is defined near the value of a. Sometimes we have something like this, which is graph A in this particular picture here, right? We have ourselves a graph. I'm going to use a vocabulary term that we are not going to talk about too much just yet, but it's something referred to here as continuous graph, right? It is constantly defined within this interval it has on here. What that just means is you could see there's an actual value here, right? We have an actual point. It's defined on that point. We have ourselves the value here, this value of f of a, which in this case is equal to that capital L for our limit. So this is where the function here is actually defined nicely on this value. Again, continuously though in this case. This graph here, which unfortunately, looking here a bit on the smaller side, but you could see we have ourselves an open circle on here. So an open dot to indicate that the function does not exist at that point, such as that example we just saw a few moments ago. This would be some type of thing we would see with that, unfortunately. An open dot. Well, we could see if we were to take the limit as to either side, we would approach that number, but due to the function, it never actually equals it. So because of that, despite the fact that this value does not exist in that particular sense, it's not defined in that number, the limit does indeed approach that. Likewise, we have, again, an open dot here. But we have ourselves a way here to define it by using this point right here, right? But again, if we just took the value of the function at this particular value a, we would get whatever this here is, f of a. But in this case, f of a and L are not the same value, since the limit deals with approaching that value, which is why this one's a bit different. Just to what you see that, even though it's defined in this case, that does not necessarily always mean it is our value. So with that being said, let's try to estimate the value here of this limit as t approaches 0 of the square root of t squared plus 16 minus 4 divided by t squared. So while we can sit here, make a table, and so on and so forth, it's usually nice to specifically look at the graph. So let me pull this up, type in a function, and then we can make our graph from that. Should be noted as I'm typing this in that you could use as I am on here, this Desmos calculator, well, graph in this case, to graph this, which, as you can see, all that do is just type in the function. It gives us our graph. Problem though with this, right? And I will try to highlight it on here. And yeah, if it wants to actually note it, I'm just going to put it in here. No, not going to let me do it nicely. All right, right here on zero. Okay, good. Now I say that and it says to go away from me. But if you see, it's here showing the value when x is 0 to be undefined. Even though it doesn't really show it nicely per se on this graph, unfortunately. But just as we saw, we could find that limit, right? And the reason why I wrote this in function notation on the screen is so then that way we could see those values from the table to be able to piece together what the heck is going on, right? So if we go from, let's start from the left side. Let's do a value of -1/2. Right, you can see we have this value here, 0.1245155 about. If we put in, let's say, -0.1, 0.12498047, yada, 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 you can see it getting close to a number. If we did, let's say, f of -0.01, even closer, 0.1249998, it's starting to approach a number, right? Likewise, if we did it from a positive direction, we actually get the same numbers. So if we did positive 0.01, we have that 0.1249998, yada, yada, yada. If we did positive 0.1, same thing as the negative, same thing with positive 0.5, right? We could see it's approaching a number, and you probably saw it when I was hovering over this graph. Well, even if I didn't find those exact numbers, if I just take my mouse and pull this point towards that value of 0, you could see those numbers. They're rounded, of course, which is why you might look at it and go, oh, it tells me the answer. It's rounded to 3 decimals on there when I do this. You could see it's approaching this value of 0.125. Same thing if I did it from the right-hand side. Starts getting close to that particular value, right? Which is why, right? Based upon that, we could say that this particular limit approaches that value of 0.125, which for us, to give a nice fractional equivalent, to be 1/8. We could do the same spiel for this particular function, limit as x approaches 0 of the sine of x over x, right? We put in 0 to these things, the sine of 0. The sine of 0 is just the value 0, and then, well, 0 over 0 again doesn't really give us anything to go by. If we were to put that into Desmos, let me quickly do that on here. The sine of x, I divide this by x. Again, if we start going to the values of on here, you could see that we are undefined at 0. Oh, there we go, 0 and undefined. But once again, if we start using those same type of thing, getting closer and closer and closer to the value of 0. If we do positive 0.1, we have 0.99833. If we do f of 0.01, 0.9999833333, same thing, f of 0.001. As you can see, you can also see on the graph, we're approaching the value of positive 1. Same thing if we went from the negative side. Negative 0.1, negative 0.1 gives us that same number. Negative 0.01, same. Negative 0.001, the same. They're all approaching that value of 1, which again, if we just choose a point, drag it on here, we could see it greatly approaching that value of 1 from either side of this. So this time, the rounding does not explicitly give the number as nicely. But the same idea, though, still applies. This particular limit as we approach 0 is not 0. It is the value of 1 in this particular case. That's part 1 of this particular lesson. Be on the lookout for part 2. Thank you.